about storage technology basics, chapter 3, and we have gone up to the half of this chapter. So I will just quickly go to the section that we stopped. Yeah, we discussed about understanding mainstream data storage nodes and network topologies, and we discussed about the differences between a centralized and a distributed storage protocols. And of course, today we will be talking about RAID devices. That's what we said we will discuss, inshallah. So I will just quickly skip to that section where RAID devices are discussed. Yeah, this is okay. This is it. So basically, we already have some idea of what a RAID device is in the previous course, maybe in forensic. Yeah, a RAID basically is a redundant array of independent disks. That's what is called a RAID. It combines many physical disks together, and then it will give you one logical drive. The type of combination or the method of combination define the type of RAID that you are using. So if you are using RAID 0, it has what is called data stripping. That means that if you have a single file, the file will be split into two. Half of it will be stored in one disk, another half will be stored in another disk. This is called stripping, okay? But it doesn't have what is called parity check, okay? Parity is a way of check, or is a mechanism that it helps basically to recover missing files or missing data in a file system. RAID 1, it has data mirroring, but it doesn't have also parities. So basically what mirroring means is that a single file will be stored in multiple disks. Okay, what do you see in a mirror? You see yourself, right? A copy of yourself, right? But in the case of a mirror, if you are missing a copy of yourself in the mirror, who cannot be found, right? But in any way, that's the idea. Okay, mirroring simply means a copy of the data will be stored in different disks. So if a disk get crashed, you still have a copy of it in another disk. So that's the idea of a mirroring. Okay, but it also doesn't have parity check. Then we have RAID 3. Data stripping is available, and it has a dedicated parity check. Now, somebody will ask, why is RAID 2 not mentioned here? Actually, in Huawei, they don't really bother much about RAID 2 or RAID 4. Okay, so that's why they simply skip it. In RAID 5, it has data stripping with distributed parity. Okay, we will see what is the difference between a dedicated parity and a distributed parity. In RAID 6, they have also data stripping with double distributed parity. So basically, it's done twice. That's the implication. Then we have other levels of RAID that combines different methods earlier mentioned. We have RAID 01. RAID 01 means that the function of RAID 0 is combined with the function of RAID 1. Okay? But then we have another one, RAID 10. RAID 10 and RAID 01 are the same, except in terms of configuration. If you're using RAID 01, you have to configure RAID 0, then you configure RAID 1. Okay?
You mean I do the 0 as a basic one?
Yes.
The primary one, and then I configure 1 as, an add-on it.
Yes. So, but if you are using RAID 10 or RAID 10, Basically, it means that you have to configure RAID 1 first, then later on you configure RAID 0. So that's the meaning. We have also RAID 5.0. This is where you configure 5 and then you configure 1 later. Okay, it combines the function of a RAID 5 and a RAID 0. While RAID 01 and RAID 10, they combine both the function of RAID 0 and RAID 1. Okay, which means that the disks would have both parity check, both stripping and mirroring function. So let's look at them together. Okay, data distribution. If you have, for example, multiple disks, disk 1, disk 2, disk 3, okay, that's what is called strip. A strip actually consists of one or more consecutive sectors in a disk. So basically, when we say a strip, okay, or we say strip A, it means that you have the same disk and you have multiple text sectors consecutively. So like this sector, this is another sector, this is another sector. You have a sector called D0, D3, and D6. They are consecutive on the same disk. Okay, so this is called strip. Sorry, this is called strip. Okay, but then we have another one, stripe, with an E. A stripe is different from strip in the sense that the sectors that makes up a stripe are not on the same disk. Okay, so you have this sector, D6, D7, D8. If you combine these sectors together, it will give you what? Stripe.
Stripe. So the stripe will be horizontal.
Exactly.
Yes, and the stripe will be vertical.
Exactly. And again, just take note that the strip is on the same disk. Okay, the multiple sectors are on the same disk. But in a stripe, the multiple sectors you will be dealing with, they are on different disks. So basically, this is another way of storing data, and it helps also to distribute the information in different sectors so that recovery or redundancy in terms of data security can be more effective. So let's discuss about mirroring. Mirroring, as I said earlier, basically means that a copy of data is stored in multiple physical disks. Okay, so you can have, for example, file 1 stored here and it's also stored here. That's mirroring. So it helps in redundancy. So if disk 1, physical disk 1 get crashed, you can have a copy of the same file, a complete file in another disk. Okay, that's why it's mirrored. But how about parity check? Basically, what we know of in parity, for example, for those that took with me previous course, we know that parity checks helps to recalculate missing files, okay, or missing fragments of a file, okay. But in Huawei, they use the aux logic gate, basically. That's the algorithm they use to calculate the parity. Okay, so it's called parity check algorithm. It uses XO. XO means that if you have similar values, the answer is opposite. If you have similar values, like this is 1 aux 1, the answer will be 0 because 1 and 1 are similar. And again, if you have 0, 0, the answer is still 0. So if you have similar values, the answer is always 0. But if you have different values, 0, 1 or 1, 0, the answer is always 1. Okay, so it means that in terms of parity check, basically if you have a file stored in disk 1, the same file in disk 2, it means that there is no need to keep such a file in the parity disk. Sorry. No need to keep the same file on the parity disk because you already have it in 2 different locations.
But the professor, it's not the parity disk. The job of parity disk is to keep the, as what you mentioned previously, that we keep the missing files.
Yes.
So it must be having the old data from the both disks.
Yes, but then when we talk about redundancy, you also have to think about how you minimize the space that you have. Okay, you have a space in disk 1, disk 2, and disk 3. Disk 3 is a parity disk. You have a file, you stored it already in disk 1, and you have a copy of it in disk 2.
So
why do you still have it in this? You understand?
Yes.
So, but in this case, you don't have this file in disk 1, but you have it in disk 2. For the purpose of parity algorithm, it can keep a copy of it because it means that once disk 2 get crashed, you can still find a copy of it in the parity disk. Okay. Again, this 0 implies that nothing is there actually. So you didn't store it here, you didn't store it here, and that implies that no need to store anything here, you know. 1, it means you have the file. 0 means you didn't. Yeah, basically.
So the job of parity is just to make sure that at least 2 disks are better.
It's just to make sure that you have a copy of the disk or fragment of it that you can be able to recover when one of the physical disks get crashed. Actually, the parity disk uses an algorithm to recover files. Okay, it uses an algorithm to recover files. So it's more or less like a backup. Though I discourage students from saying it's a backup. Okay, because it doesn't, in the real sense, it doesn't actually store the file. Rather, it calculates the fragment of the file and use it to recover the file. Okay, it uses an algorithm to recover the files, basically. So that's what it does. So it's not, it helps in backups. Yes, it helps in backups, but it's not a backup in the real sense that we know it. Do you understand?
Yes. We can say it's backup or it's retrieve the missing values.
Yes.
Or the missing data. Yeah.
Yes. So let's look at this. You have 0x0 is 0. 0x1 is 1. 1x0 is 1. 1x1 is 0. Yep. Then we have what is called a hot spare and reconstruction. Okay. So basically what it implies, if I can summarize what it implies here, a hot spare, from the name spare, if you have a spare tire, what it means?
That means I have
a backup.
I have a backup. I have spare.
So yeah, so basically that's what it means. Okay, a hot spare is a disk, okay, that becomes a spare to another disk. It works as a replacement to that disk, okay, and it helps in reconstruction of information that are missing in a crash disk. So if you have For example, this disk get crashed A0 in a RAID device. If it was with a hot spare, it means that you can actually recover the content of A0 from the hot spare, because it's actually a spare of it. Okay, so spare works in two ways. That's what we call global, and that's what we call dedicated. A dedicated hot spare is only assigned to a dedicated physical disk. For example, if this hot spare is dedicated, it implies that it can only recover A0. So if A1 get crashed, you actually don't have it here. You don't.
It will be only
Because
for the
actually it's
dedicated one.
dedicated to a specific disk. Okay? So, but if it's a global type, okay, it can be assigned to a group of disks.
From the name.
Yeah. So basically what it means that if this dedicated hot spare is assigned to this group of disks, any one of these three get crashed, you can get replacement.
Professor, what if two get crushed?
If two get crashed, you can still reconstruct it because this is a hot spare. I guess it will be able to recover it, especially with the parity. The parity can help a lot here. Because if you have a content of one, you can reconstruct the other one from the parity check.
Okay.
So this is another function for a disk in a RAID device. I believe maybe this concept is new because this concept is not discussed in our previous course. So this concept is new.
So I have a question now. What is makes the hot spare is different than parity?
Very good question. A hot spare contained basically a backup.
It's
A
real
parity,
data.
yes.
You mean for the complete data?
Yes, it's a spare.
Yes.
Okay, but a parity uses an algorithm to compute missing information.
Only the missing information, the
Yes.
missing data, but that one, the hot spare will be the whole data.
Yes. Actually, the parity can as well compute the whole data. It all depends.
The whole data of the file,
Of a
but
disk.
not the whole data of the whole.
Of a disk. Of a disk, it can.
Also it can.
Yeah. If you
If
go
it's
back,
zero.
yeah, if you go back a step back, for example, can
If
we?
it's zero, Professor.
No, this is no, I think it cannot, because this is not a disk actually per se. This is a sector of the disk. So, like for example, you have 0 and 1. These are sectors. Okay. Yeah, actually, yeah. That's what we know in digital forensic.
Yeah,
It computes the sectors, not the complete disk. Yeah. So you're right. So let's go back to common RAID levels. We talked about data stripping as the first one, RAID 0. So physically, this is how it works. Okay, you have two disks, disk 1 and disk 2. Disk 1 have two contents, D0 and D2. Disk 2 have D1 and D3. Okay, the logical disk, because the idea of RAID is combine physical disk into one logical disk. So the logical disk is going to contain both this and this. Okay, so you have this complete. So you have D0, D1, D2, D3. Okay, so that means both are combined. Now, the idea here is that if you have a single file stored in this RAID device, okay, this file will be splitted into two. Half of it will be stored in disk 1, and the other half will be stored in disk 2. That's the meaning of stripping. It's stripped into two. Okay? So it implies that if disk 1 get crashed, you cannot recover that file.
Could be encrypted.
It's corrupted, yeah.
Corrupted, yeah.
If disk 2 also get crashed and disk 1 is still functioning, you can still not get the file because half of it is gone. Okay? Now, somebody will say, okay, if we talk about RAID, why is it used this way? It is used this way because it gives you more space, but it's not designed for redundancy. Okay, so let's look at it. If this is 1 gig and this is disk 2 is also 1 gig, it means that the logical disk is what? 2 gig, right? Yes. Very good. But now let's look at the second one. RAID 1. RAID 1 have a different design because it's designed for the purpose of redundancy and recovery. Okay, so that's why it uses mirroring. So if you have disk 1 and disk 2, two different disks, right? The logical disk will give you the same disk. Okay, so if you have a single file, you store the file in disk 1, the same copy of the file is stored in disk 2. Okay? The same copy of disk is stored in disk 2. It implies that if disk 1 get crashed, you can actually have a copy of the file in disk 2. Do you understand? Okay. Now, the difference is that if disk 1 is 1 gig and disk 2 is 2 gig, is 1 gig also, what is the size of the logical gig? 1 gig. But in this case, in the RAID 0, the logical disk is what?
2.
Is 2 gig. If disk 1 is 1 gig and disk 2 is also 1 gig, 1 plus 1 will give you 2. But in mirroring, is different. It's 1 or 1, not 1 and 1. Okay? Therefore, the size of the disk in RAID 1 will not change. So if these two are 1, 1, you will still get the logical disk to be 1. This is the idea. Let's look at RAID 5. Sorry, I don't have the mouse today, and I cannot remove this one. I think I prefer to use the mouse. Let me see if I can. Can I borrow this for a minute?
Of course.
It is removable. Yeah.
Professor, the RAIDs are inside the physical memory. Am I right?
Yes.
It's inside the physical memory. For example,
disk, not memory.
The disk is not the memory?
No. Memory is the RAM.
No, I mean the RAIDs. It's the memory.
It's the disk. It's the hard disk.
It's the hard disk.
Yes. There's a difference between a hard disk and a memory, right?
Yes.
Am I right?
Yes. Yeah.
The memory is the RAM.
The RAM.
The RAM is temporary.
Yeah.
Yeah, so this one we're talking about the permanent type.
But the RAM, it's non-volatile.
Yes, yes. So that's the one we are referring to, the disk, the hard disk, the one that has SATA, SSD.
SSD and
yeah.
SATA.
So these are the ones. These are the ones that I use for it, not the RAM.
SSD also, Professor, it has a RAIDs.
Yes.
But you know, there's now with the new technology, the SSD become very small and
yes.
very, very light.
And very high capacity.
Yes, very high capacity.
Yes, yes. That's the theory of computing that you learn in computing fundamentals. That over time,
every year.
The
Yeah,
processor and the hard
every
disk
2
will be
years.
smaller,
Will be smaller,
but
yes.
the capacity of them will
Will be,
increase
yes,
by
will
double
decrease.
after every 5 years.
Yeah.
So that's what is happening actually. So let's look at this. I think we discussed 1201. Let's say RAID 5. RAID 5 has a parity. Actually, parity starts from RAID 3. But in this slide, Huawei decided to skip RAID 3, okay, and just go to 5. Okay, so basically you have a disk, for example. For you to have RAID 5, first of all, it means that you must have a minimum of 4 disks. Sorry, 3. Did I say 3? For this 3 disks, 1, 2, 3. Yeah, 3 disks. You need a minimum of 3 disks.
And it starts from RAID 3, so you can do it from RAID 3, it has 3 disks.
Yes. You need a minimum of 3 disks, okay? Because some sectors of the disks are designed for parity. Okay, and parity, as we mentioned, uses the OX algorithm, okay, to recompute missing information. Okay, so you can have this physical disk, disk 1, disk 2, disk 3. And disk 1 has a parity, disk 2, sorry, disk 2 has a parity, and disk 3 also have a parity. Okay, so it implies that missing information from either of or this can be recomputed. Actually, they all work in harmony. Okay, basically the disks work as a logical disk, one single disk. So you can have this sector 0, 1, 2, and 3. Okay, now you always have to ask the question, what if it fails? This is the question that will always help you to remember how it works. Okay, you can say, what if disk 1 get failed? Can we recover disk 1 if it fails? Because we have two sectors, 0 and 1. Yes, we can recover it because we have a parity in disk. We have two parities in disk 2 and disk 3. Likewise, if disk 2 fails, this is only the sector that is missing, D1. We can as well still recover it because we have a parity check in disk 3. Now the idea is in disk parity in RAID 3, the one that was skipped, it has a dedicated parity. A single disk is dedicated to parity only. Other disks are normal physical disk. Okay, so we asked the question in RAID 3, what if the parity disk is the one that fails?
This is why they create another sector to be another parallel parity.
Exactly. So if the parity disk is the one that fails, it means that missing information may be difficult to recalculate in other disks. Then they created 5 and decide to put the parity check in multiple different disks, so that if a parity check disk gets crashed, you can still use another parity checks disk sector to recalculate basically the missing information. So this is the logical idea here. At RAID 10. RAID 10, as we said, is a combination of 0 and 1. Or let me say 1 and 0, because you have to do 1 first in this case before you do a 0. Okay? Now, this is 1 and this is what? 0. In 1, we simply do what? Mirroring. Okay? So like now look at it. These are all your multiple disks, physical disk. Okay? So 0, D0, D0. You mirror D0, D0, you have D0 still. Right? So because you have to start with RAID 1. Okay, this is the idea of RAID 1. You have D1, RAID 1, it will give you D1 actually. Okay, so we only like have the same logical disk. Likewise, D2 will still give you D2. D3 will still give you D3. Not 2 of D3, no. It's only 1 D3 you will get because it simply mirrors, right? So you have finished with the configuration of 1, RAID 1. So let's go to configuration of 0. In 0, if you look at this, it combines and you get double the size basically, right? So if you have D1, D2, D3, D4, and you are using RAID 1, what you have? What are you going to have?
Again, question.
If you have D0,
Okay.
D1, D2, D3 as the disk, physical disk, and you are configuring it as RAID 0.
RAID 0 will
yes.
be the same. D0, D1, D2, D3. Sir?
Yeah, right, but not the same. It's addition of them, right? So you simply add them. D0 plus D1 plus D2 plus D3 will give you the logical disk. This is the final logical disk. Okay. Now this configuration will help you to do both mirroring and data stripping at the same time. It increases the size of the disk and at the same time create what we call data security for redundancy. Okay, so if in case this get crashed, you can still get it back, okay, through mirroring. But then that means that like you have redundancy, right? At the same time, you have more space because now the space you are using is the space of D1, D2, D3, and D0. Because the difference between 0 and 1 is that 0 have more space but no security. But 1 has security but no space. Any question? Working principles of RAID 6DP. That's another RAID called 6DP. Okay, RAID 6DP simply means RAID 6. Okay, but double the parity. Double the parity. That's DP. Okay, double the parity is what is called DP. So let's look at it. What you have parity checks 0 to 3. Okay, now look at it. Where is 0? P0. P0. Okay, so you have this one. No. I'm looking for.
P0 is the second one, Professor.
Yeah, I just saw it now. Sorry. So P0 to P3. P0 to P3 is horizontal. Now, I will need my what is it called? My pen.
Professor, it's not vertical.
No, it's not vertical. It's horizontal. Look at the name of the disk. Horizontal parity check. Okay, so if that's the parity check according to what is called strip. You remember strip?
Yeah.
Strip is what?
The strip, yes, is
horizontal, right? So this
horizontal.
is the disk for P0. Okay, now what it means is that if any of these sectors that are located in different disks is bad, you can actually calculate it with P0. It will do for you the parity check from P0, and you can recover that sector or that missing file or that missing information that is missing on either of these disks. Okay, so also for this, P1 will do this one for us. P2 will do this one for us. And P3 will do the remaining ones. Do you understand? So now, the idea here is that RAID 6DP has two types of parity. One is horizontal parity, and the other one is called diagonal parity.
The vertical.
The vertical. Diagonal. Not vertical, actually. Diagonal is not vertical. If you say vertical, it's like this.
Yeah.
Horizontal is like this. Vertical is here. But diagonal is the other way.
Yeah, yeah.
Cutting across.
Is it, Professor, that mean that DP0 will have exactly a copy of P0? Because P0, it has D3, D2, D1, D0. Am I right?
No. Now this is the thing. This is the thing. I will need to, if you understand this first one, how the horizontal parity disk works horizontally, I will need to delete what I wrote so that we can go over for the other one. Okay? How do I delete it? This code. And then I'll do it again. Easy. Yes. So the diagonal parity deals with the disk diagonally. Okay? So if you are looking for DP0, this is what it takes. Sorry. I need to bring back my pen. So it will take this 0, 1. It goes here and takes D5, and it goes here and take D10, and it goes here and take D15. This is what is called diagonal.
So all of this will be DP0.
Exactly. DP0 can calculate all this. Where is my mouse? Where is it? Yeah, it's back. So it will give you DP0.
Okay. Now I understand.
Okay. If you are looking for DP1,
it
will start. Look at yeah. Another thing is, look at how they put the colors. This is light blue. You can see all the disks in light blue. That means DP0. Now look at the green. Where the green starts from? It starts from here. And then this. And then it calculates this. And then it will calculate this for you. Oh, sorry, I no need for this one. This is a parity disk, sorry. I say no need for it. It's a parity, yeah, but it's green also. It takes it, no problem, it's green. It takes it. So this diagonal. Okay. If you are looking for this one, D2, you go this. And then if you are looking for this, you go like this, and it come back and take this.
Look, it's confusing.
It's not confusing.
What if there is more than 4 disks?
If there is more than 4 disks?
Yes.
Well, this disk, it starts from minimum of 4. You can have 5 disks, no problem, it will still work.
Okay.
The important thing is the last 2 disks are dedicated for parity. One is for a horizontal parity, the other one for a diagonal parity. Okay? The first 4 disks are the physical disks that contain the actual information. Okay? Now let's look at another thing. How did we calculate P0? You remember? P0. P0, we said this plus this plus this plus this. You can see now. P0 equals to
D0.
D0 aux D1, aux D2, and aux D3, right? Because it's using the aux. Now, if we had to calculate this one, dp0, dp0, the equation is diagonal, as we say. So we take dp0, you see it? Yeah. Equals to what? D0, D0, D5, D10, D15. That's the equation.
So therefore, Doctor, I think DP1 will be 1, 6, 11, 16.
DP1 will be 1. Where did you get 11 from?
D11.
6 and 11.
From this.
No, where did you? I'm asking. He was right. 11 is there,
Yeah.
but why did you jump this? It's diagonal.
Start from 1,
Yes.
6,
Yes.
11,
Yes.
16.
16.
Because if you talk that parity, then some disk will not be included in the double parity.
Actually, yeah, okay, I understand. I understand his idea. It's actually just a matter of leveling. Okay, whether you call this D16 or you call it as it's labeled already, P3 is still the same. But now the thing is, there's an advantage to this. Okay, it implies that you actually have parity inside parity. That's the double parity. Okay, you are trying to get a parity of this, but then you included another parity to it. That's the double parity. Do you understand? I don't know if it makes any meaning.
I understand Khalid's idea. I understand Khalid's idea. He was adding 5 each time.
No, it's just a labeling. Actually, labeling doesn't matter. It's okay. If you call it 16, it's okay. When he said 16, I was confused initially, but I later understand where he's going to, because D15 is the last one, so he added 16 there.
But doctor, it's adding 5 each time.
5,
5, 10, 15. Then will be 1. 1 will be added to the 5 will be 6. 6 I'm gonna add it to the 10 will be 11.
Oh, I get it. Yeah, I understand what you're doing. But then
you're gonna add the 2.
now let me tell you something. If you have 5 physical disks,
It will be added 5.
it will still add 5. I think in this case it will add 6. Because the numbering is like this, okay? So if you have 5 physical disks, you have additional disks here. So that disk will take 4, and here it will be 5. You come here, 0, you have to add 6. You understand? So it will,
Yeah.
it will add more than 5.
Yeah, it will be different with
Yes,
the,
yes.
with the
So it depends on the number of disks. So don't just assume always 5. No, depend on the number of disks. But this is just the general idea. But then Huawei, they try to increase they believe that all the rate methods that we mentioned have some problems. Okay, they have some issues. Number one is that they said that it has like prolonged time of construction, prolonged time for construction of the disk. So it takes a long time to recover the information if you're using any of those methods that we mentioned. And of course, some of the methods still data are lost, especially if you are using stripping. Okay? And the issue of fault tolerance. So they introduced this RAID 2.0 to help to solve these problems. And RAID 2.0 Plus, which provides basically smaller spaces as small as tens of kilobytes, okay, to help basically to reclaim the missing information. So Huawei, they have the Huawei 2.0 Plus. That's one of their latest technology that they use for these RAID devices. Now let's look at how it works. This is how it works. You have the disk, the hard disk. Let's say these are the hard disk. If you are using SSD, you have multiple hard disks, right? You want them to work together as one, right? That is the idea of a RAID. But then, to make it more effective in reconstructing information and getting back information, they try to make sure that they split these spaces into what is called chunks rather than strips and stripes.
So it's different method. We call it chunks.
Chunks meaning that it's very small. A chunk is actually 64 kilobytes. Sorry, MB, megabytes, right? A chunk is 64 megabytes. But then if you go back to the other disk that we use, if you have 1 terabyte of gig, let me take you back. Like, let's look at this. If disk 1 is 1 tera, and it's only split into what? 1, 2, 3, 4, 4 sections. How many do you have? Maybe about 200 and something gig. So reconstructing 200 and something gig space in a parity, it takes longer time because it's big. Okay? But if you are dealing with chunks, which is just 65 megabytes, it's easy to reconstruct and it helps the performance of the system in terms of the speed. So this is their idea basically. They don't want to be known to be copying other people's ideas anymore. Sorry, I'm recording.
So, Professor, you remember when you teach us in the forensics,
Yes.
don't leave any evidence?
Yes.
See, now you are leaving evidence of yourself.
Anyway, so basically what happens here is that if this is 1 tera, 1 tera, 1 tera, 1 tera of SSD, okay, so this will be split into chunks, which are small. So you have a lot of chunks, then the chunks will be grouped. Okay, so you can have groups of chunks, groups of chunks, group of chunks. Chunks are called CK. Group of chunks are called CKG. Okay, then there's another thing that is called extent. So group of chunks, they have extent. Extents are basically smaller than a chunk. It's just about like 4 megabytes. Okay, so it is this extent that will now be stored in what is called LUN. LUN is, I think we learned about LUN previously, logical unit number in the disk, in the logical disk. Okay, so basically these chunks will be given numbers that will be used to identify them. Okay, so therefore, if a chunk is missing, basically you can be able to recover this chunk from another disk or from the logical disk as fast as possible, because not just that it is a small unit, but it's also identified with an address. Okay, so this is the idea of 2.0 plus. So I try to add this to the slides. We have the SSD. It will be split into chunks, which is about 64 megabytes, and the chunks will be split into chunk groups, and then it will be split into extents. Extents are as small as 4 megabytes. Okay, extent will be assigned LUN, logical unit number, okay, which will be used to identify them. And this will help in recovering, and it improves also the performance of the system, because now the system actually just need to reconstruct something very small rather than a large chunk of a portion of a disk, basically. So this is the idea.
This process, we call it block virtualization.
Yeah, block virtualization in 2.0 plus. Yeah, so I put the advantages here. It's easy to construct, quick reconstruction, and it has automatic load balancing. I really want to finish the class quick today, but the information needs to be studied gradually, you know. So let's look at SCIA. SCIA is SCSI. We have had this word before. Small computer system interface, right? Is actually a connection box between a storage device and an external disk. We studied this both in the first section of this chapter, and also in chapter 2 we studied this. Okay, if you remember, in chapter 2 we talked about JBOC. You remember JBOC in chapter 2? JBOC is used to connect multiple physical hard disks to a server, right? So in between, if you go back and check that diagram, in between we have the CSSI bus in between them. Let me see if I have this diagram in. I'm not sure if I have it here. Yeah, this is the JBoard. Just a bunch of disks, and this is the SCSI card. Okay, so this one is external. Okay, it's just like an external device. You arrange hard disk on it, okay, and then use the SCSI card to connect to the disk. This disk is internal in the system or in the server. Okay, so it's used to basically connect external drives with the hard disk of a computer, basically. But in this section, we want to discuss more about it. Okay, so if you just want to remember, it's used to connect between hosts and peripheral devices that are basically external devices. This is the most important thing. How it works is that the SCSI bus look like this. Okay, you can have a number of disks, and then you can have a connection of the SCSI box to any host. It can be connected to any host as an adapter, and then data can move through the bus to the external disk for write or for read with the reverse keys. Likewise, it has a number of applications. SCSI application layer, layer-to-layer connection. It has what is called the CS connection. But between SCSI transport layer and SCSI transport layer, it uses a command or a data. Between SCSI interconnection layer and SCSI interconnection layer, you have a bus connection. So these are the different connections that it has basically. What you need to remember here is that if you have a host, server, or anything, or a data center, and you need additional device as storage space, then you may need the SCSI card connecting as a bus to it, basically. So this is where it's this how it's connected. You have the SCSI instructions here. Okay, it can be connected to TCP/IP layer and then to the physical layer. However, that's what we call iSCSI. iSCSI simply means internet, internet small computer system interface. I need to put some of this additional information. They are not in the original slide for the student to be able to recall what it is basically. So the iSCSI uses internet connection. That implies that it's in between a SCSI bus and what? IP, internet IP, basically TCP/IP layer. So that's where it is, iSCSI. The iSCSI have two different functions. That's what is called the initiator and a target. Okay, both of them, if you check, they pass through the TCP/IP layer because we are talking about the internet. Okay, so the initiator has the iSCSI layer that generates command description blocks, which are also called CDBs, and transfers them to iSCSI layer. So basically from SCSI layer to iSCSI layer, you need the CDBs. Then from iSCSI layer, it generates iSCSI protocol data units, which are also called PDUs, and send them to target over the internet using an IP, of course, IP network. So this is the initiator. For the target, it simply uses iSCSI layer to receive PDUs. PDUs, of course, are protocol data units, and send them to CDBs, which are command descriptor blocks, to the SCSI layer. And then SCSI layer interprets the CDBs and gives responses when necessary. Basically, these are the steps for each of these two different units of the iSCSI protocol. So the initiator basically sends, okay? The target basically receives, okay? The initiator basically sends in form of what is called CDBs, command descriptors, and PDUs, which are protocol data units. Target received in these same forms, but now it's receiving both PDUs and CDUs. Basically, this is the interpretation of the functions of the HCIA initiator and target. Let's discuss. We learned the SC SANs and IP SANs. Who remember this? Last class. The SAN disk, the NAS disk, you remember? NAS and SAN disk? Yes, you should remember. The NAS and SAN disk. The NAS, we said, is a protocol basically for files. File systems. NAS. The NAS. But the SAN is more general, basically. Okay? And the SAN is divided into two types. FC SAN, that's fiber channel type, and the IP SAN, which is basically IP type. It uses IP. Okay, so we learned this. Okay. To convert, yeah. In diagram, I think we show that the IP SAN switch, you will see it in blue, and the fiber optic types is in yellowish or orange type. The diagram that we showed last semester, last class.
So again, the NAS is.
You need to go back and revise that table. Let me take you to that table. It will help you. The table was not originally on this slide, but I created it, I put it. Yeah, this is the table. It will help you a lot. Okay. The SAN storage and the NAS storage. Okay. Let's go through it again. SAN storage uses block level, while the NAS uses file level, because basically it's a protocol for files, file generation, file transmission, and stuff like this. Because it deals with files, it uses protocols that are related to files, like network file system, UC file, NFS, or CIFS, common internet file system, you will see file, or FTP, file transfer protocol, right? So basically these are related to file, that's why it's on the NAS. For SAN, it uses the fiber channel, the HCIA, and the FOCE. We will discuss this in the next slide. This one, the SAN has very good performance, but low latency, moderate performance, network dependent, depending on network scalable and moderate scalable. This one is data visualization based, while this one mostly is file sharing, backups, media storage. Yeah. Expensive for SAN, while this one costs a little bit okay. So this is the difference. These are the differences. But if you want to see it in a protocol type or topological type, you can revise these slides. Let me see. Now you can revise the next one, this one. Okay, you can revise this one. Now you remember, right? Just to remember. Yeah, so let's look at fiber channels and TCPs. Now we know that the SAN uses fiber channel, which we call FC, and it also uses IP, which we call IP SAN. FC SAN or IP SAN.
Okay.
Right? These are two types. We just saw it in the other slide, in the tabular form. Now, the world is thinking of how these two protocols can work together. We don't have to have them like separately. We want them to coexist together. Okay, you can see we try to like show that we want to connect this and this coexist. We don't want them to be separate. Each one of them have a good function. We want the functions. We want them to work together. So in trying to make sure these two protocols work together, they created two ways of connecting them together. One is called IFCP. That's the first one here. The second one is called HCIA. These are the ways. The first one uses the fiber channel in a TCP. That's why it ends with a P.
Protocol.
Yes. The second one is fiber channel with Ethernet connection. That's why it ends with E. Okay? So these are the ways. Now, let's look at the first one with TCP, TCP/IP. Okay? So therefore, we need a switch called IFCP switch or gateway, basically. And we need to connect it in between the two protocols that we want them to connect and coexist together, which is the IP SAN and the FC SAN, right? So now this is the IP SAN, the IP, and this is the FC fiber channel. In between them, we just need this switch or this gateway. This is the gateway. And when we connect them, okay, it will help us to be able to transfer data between one point to another on the network. So also we need it here. So the name of the switch also is the name of the, did I say switch? Sorry, gateway. It's also the name of the protocol, IFCP. IFCP simply means Internet Fiber Optics TCP/IP. So this is the channel, fiber channel, and this is, so you can device here, you can have your storage device here, and these two protocols can coexist together because you have the FC and you have the IP. Yeah. So look at it again. This is the FC. This is the IP, TCP/IP. In between, you have the IFC. That's the gateway switch that you need to connect the two of them together, right? So therefore, basically they can coexist together with the help of the IFCP gateway. The other one that uses the Ethernet switch. So it's like this. You have the Ethernet data link framework, okay? And okay, there's something I forgot to mention. This HCOE, it helps for encapsulation. Not just this, I think there's another one that helps in encapsulation I didn't mention previously. I think I skip it. Yeah, HCIA. HCIA is, it has encapsulation as against normal SCSI. SCSI doesn't have encapsulation, but if you have HCIA, it has encapsulation. I forgot to mention this. So also this, where is it? Yep. So this one, it uses simply Ethernet. The full name is Fiber Channel over Ethernet. That's the full meaning. Okay, it allows the transmission of LAN, okay, and FCSAN data on the same Ethernet link. Okay, this reduces the number of devices, cables, and network nodes in the data center, as well as the power consumption and cooling loads, simplifying management basically. And it also gives the encapsulation of data SC data frames. So this is how the Ethernet cable that is used for this type of connection. This is how it looks like. Okay, it have the vibe call, video streaming, block storage, service flow IP address, and stuff like this. Yep. So the protocol look like this. Oh yeah, that's good. This is the last slide. Alhamdulillah. I'm happy I'm finished. The protocol look like this, okay? The upper layer is for the fiber channels because we are trying to link the fiber channel and the Ethernet, right? And the lower layer is for the Ethernet. So in the fiber channel protocol layer, it has three different layers: FC2, FC3, FC4. In the lower layer, it has the physical, the MAC, and the FCO layers. Yes. So basically, these are how these are divided, and then you can have your encapsulation. It works very well. Okay. In FC2 here, that's where the encapsulation happens, and above layers into Ethernet packets for transmission. So from FC2 upward, you can have encapsulation here. Otherwise, FC0 and FC1, there isn't any encapsulation. This transmits into the Ethernet protocol layer. For the Ethernet protocol section of the FCEO protocol encapsulation that helps us to combine the functions of FCSAN and the IPSAN together so that they can work in harmony and coexist together as we want it. So basically, that's the last slide. What are the application scenarios of FCEO? What are the application scenarios of IFCP? These are questions. Which of the following statements about FCSAN are true? Fiber channel switches are required. Can you remember this? Because it's last class, not today. Okay. FCSAN requires fiber channel switches. That is true. Okay, that's the I think that's is it the blue switch or the orange switch? Let's go back. Let me show you. You see it is the orange switch. The blue switch is for the IPSAN. Okay. Oh, sorry. The blue switch is for the IPSAN that uses Ethernet switch. This is the blue switch. The orange switch
for
fiber optics. We always need this. Okay. We need this for FCSAN to work. We need this for IPSAN to work.
And we merge it together to become.
Yeah. At the end, yes. We can merge them together, yes. I'm just trying to make you to remember. Maybe you use the color to remember. You know? No, of course, nobody will ask you about the color. But it's just trying to tell you that these are two different types of switch. They are not the same type of switch. Okay, this one is a fiber optic switch. The other one is Ethernet switch. Yeah. So which question? Yeah. So this one is true.
first one.
Yeah, Ethernet switch are required for FC SAN. No, the blue switch is not required. It's only the orange switch is required, right? For FC SAN. This one is
This
for
one will be the
IP
blue.
SAN.
Like,
For IP SAN, okay? Fiber channels links cannot be used between storage devices.
false.
This one is false. Data packets comply with fiber channels protocol stacks. This one is true. Data packets comply with FC protocol. Yes, yes, of course. Yeah, so A and C should be correct. In my estimation, this A and C is correct. Okay. The performance of SATA disk is better than that of SAS disk. True or false?
True. Performance.
In terms of performance, and I mentioned this several times even.
The performance will be SAS is better, but in the storage SATA.
Exactly. SATA has more storage. But when you talk about speed, performance,
Speed, that would be SAS.
so this statement is what? It's false.
False. Yeah. Performance will be.
The statement is false.